For our calculus final project, we have decided to research the calculus behind baking an angel food cake. Our objectives for this project are to find when the angel food cake is ready to be eaten by using Newton's law of cooling, and to find the volume of the angel food cake using double integrals and the disk method. Our first objective is to validate the cooling time given on Martha Stewart's recipe for angel food cake. According to Martha Stewart's website, the cake should take approximately 1 hour to cool to the optimal temperature for eating.
This is the data we've gathered by taking temperature readings in 10-minute intervals. This slide shows our data in the form of a graph. The name of the graph is the temperature of the cake against time. The y-axis shows the temperature in degrees Celsius, and the x-axis shows the time in minutes. This graph also shows that the function is an exponential decay function.
We are going to use the Newton's law of cooling equation. The temperature in terms of time is equal to the surrounding temperature plus, open parentheses, the initial temperature minus surrounding temperature, close parentheses, times e to the negative kt. Our surrounding temperature was 20.6 degrees Celsius and our initial temperature was 80 degrees Celsius. We are going to calculate the temperature after 60 minutes.
In order to find the temperature at time t, we first need to find K because it's an unknown value. To find K, we will use the initial temperature, which is 80 degrees Celsius, and the temperature after 30 minutes, which is 40 degrees Celsius, and this data is taken from the data table in slide 5. Here are the calculations for the Newton's law of cooling problem. In step 1, we plugged in all of our known values. In step 2, we simplified the expression from step 1. In step 3, we divided both sides by 59.4. In step 4, we took the natural log of both sides. In steps 5 and 6, we divided both sides by negative 30 in order to obtain the value for K, which is 0.037301. Now that we've found K, we only have one unknown variable left, which is the one we need to validate the cooling time given by Martha Stewart's recipe. Let's find what the temperature of the cake is after 60 minutes of cooling as given by the recipe. In the first step, we plugged in all of our known values, including the K value that we just calculated in the last slide. In step 2, we simplified the expression, and in step 3, we obtained the temperature after 60 minutes of cooling, which is 26.936 degrees Celsius and translates to 80.4848 degrees Fahrenheit.
After these calculations, we concluded that Martha's instructions for cooling were relatively correct. We say that she was only relatively correct because after 1 hour, the cake should have cooled to a temperature of 26.936 degrees Celsius if you follow Martha's recipe instructions for cooling time. This temperature of 26.936 degrees Celsius was the temperature that we calculated using Newton's law of cooling after the 1 hour cooling time suggested by Martha. Basically, Martha Stewart is saying in her recipe for the cake that after 1 hour of cooling, the cake should be ready to be eaten at the temperature of 26.936 degrees Celsius. However, after doing some research on numerous websites, we found out that angel food cake is ready to be eaten when it reaches room temperature. Room temperature is 25 degrees Celsius. So Martha's estimation for cooling time is an underestimation. So if you are using the Martha Stewart's recipe for angel food cake, you would need to let it cool for a little bit over an hour to let the cake reach optimal temperature for eating, which is a cool temperature of 25 degrees Celsius. Our second objective focuses on finding the volume of the angel food cake using a new application of calculus, double integrals, and a familiar method, the disk method. First, we will find the volume of the cake using the disk method. Here is our data. The volume of the cake is equal to the integral from a to b pi r squared dy. In this case, we are using dy because we are finding the volume of the cake in respect to the y-axis. We found that the height of the cake was 3 centimeters, so a will equal 0 and b will equal 3. We measured the radius of the cake to be 10.9 centimeters. When we put all these values into our equation, we get that the volume is equal to the integral from 0 to 3 pi times 10.9 squared dy, which is equal to 1,119.758 centimeters cubed.
Now we're finding volume of the cake using the new application, double integrals. On my right is the two-dimensional graph of the base of the cake. The vertical axis is the z-axis and the horizontal axis is the x-axis. And the radius of the cake is labeled 10.9 centimeters as shown. Moving on to the left side is the three-dimensional graph of the cake. The axis with lines that seem to pierce the center of the cake is the y-axis. The other two axes perpendicular to the y-axis are the x and z-axis. And lastly, the height of the cake is shown as 3 centimeters. Here are the calculations for finding the volume of the cake using double integrals. In part 1 of the working as shown on the left, we find the expression for the base. The equation of a circle with a center at the origin is x squared plus z squared equals to the square of a radius, which is 10.9 squared. We subtracted x squared from both sides of the equation, and then we express the equation as a function of z by taking the square root of both sides of the equation. The expression for the base of the cake is 2 times the integral from negative 10.9 to 10.9 zx dx. The reason why we multiply the integral by 2 is that the integral would only give half of the circle, and we want the area of the full circle. Moving on to part 2 of the working as shown on the right, we find the volume of the cake. The volume of a cylinder is the product of the base, area, and height. We plug in the expression for the base area we obtained in part 1 and find the integral expressing height. The reason why the expression for height is an integral from 0 to 3, 1 dy, is that we are integrating from a straight line graph with respect to y. In the next step, we combine both integrals. After that, we introduce the identity of function z to get a value of 1,119.758 centimeter cube.
As it has been shown by the following calculations, the correct volume of the angel food cake can be determined using either double integrals or the disk method. Let's summarize what we've learned. Martha Stewart's approximation for the cooling time of the cake was incorrect. Using Newton's law of cooling, we found that after 1 hour of cooling, the cake would cool to 26.936 degrees Celsius. However, we wanted the cake to cool to the optimal eating temperature for an angel food cake, which was 25 degrees Celsius. So we would have to let the cake cool for a longer amount of time to reach this temperature. Then, we found the volume of the cake using a simple method of disks and the complex method of double integrals. Both methods got us to the correct volume of our cake, which was 1,119.758 centimeters cubed.